Hi everyone. Today I'm going to be working through the examples from exercise 1.4 from your Jack Plus textbook, and this is quadratic functions. So look, there's quite a lot of examples. I might spread them across two videos. We'll just see how we go. Let's look at worked example 9, and they're asking us to factorise, not solve, the quadratic expressions. Notice that we can't solve it because there is no equal sign, so, well, hence we're just factorising. So don't go on to solve because then it will be wrong. When I look at this one, I see that it's probably going to be our identity of a squared minus 2ab plus b squared. And of course that will factorise to a minus b squared. I think that because, well, there's something squared here, there's something squared there, there's three terms, and I'm guessing that the middle term will be 2ab, or negative 2ab rather, and that's what I'm going to check out. So let's let a equal 3a, not 3a squared or not 9a squared, and then b is going to be, well, the square root of 16b squared, which is going to be 4b. So this was, a was the square root of this and b was the square root of this, because 9a squared is a squared and 16b squared is b squared. So now what I want to check is if negative 2ab is going to equal my middle term. So let's do that. Negative 2 times a times b, and that's going to give me negative 2 times 3a is negative 6a times 4b, and yes, negative 24ab. So negative 2ab is negative 24ab in this case. So that means that, yes, the identity works. So now what I can do is just factorise it by subbing these in. And I end up with a, which is 3a, minus b, which is 4b squared. So that would be my factorised form. It's a little confusing because in our identity we've got a and b, and then in our example we've got a's and b's as well. So just don't get confused with that. Okay, moving on. The next one from example 9, we're factorising another three-term thing. Expression. So look, the thing you should always think of is cross multiplying, and that's most likely going to work unless it's a complete the square example. So this one looks like it should be pretty straightforward. Let's take a look. 3x times 2x will give us 6x squared, and then let's see, 7 times 1 is of course 7. We've got to get to negative 17. So negative 7 times negative 1 will give us positive 7. And then 3x times negative 7, well, that's going to be negative 21. 2x times negative 1, that's negative 2x. So that's not going to work. But if I swap them over, I reckon this one will work. So we get 3x times negative 1 is negative 3x. And 2x times negative 7 is negative 14x. And that does give us negative 17x. And look, I would do this line of working out every time. It may not be necessary for you. You might think it's easy enough, but it saves making silly mistakes, especially if you're in a rush. So now when I factorise this, it's this and this. So 3x minus 7 and 2x minus 1. And I'm not going to solve it. I'm not going to make it equal 0 and solve for x because I cannot. It doesn't say equals anything, so you are unable to solve. And plus it tells us to factorise. So that's that one. Let's move down. Okay, so now we have, using an appropriate technique to to factorise this quadratic expression. And what I see is that, well, 2t and t, and any factors of 14, and look, it would make even more, it would be even clearer if I take the 2 out. If I try and cross multiply, there's going to be no factors of negative 7 that when I add together with the factors of t squared will give me 4t. So this tells me I need to complete the square or solve via the quadratic formula. So I'm going to complete the square here, and I think you want to practice with both techniques, the quadratic formula and completing the square, because people tend to like the quadratic formula better, but actually complete the square can be a lot easier sometimes. So let's see, completing the square, t squared plus 4t plus half of our middle term, half of 4 squared. And this is making the square. So this is a squared plus 2ab plus b squared, because eventually what we want to factorise it to is a plus b squared. That's the whole idea of completing the square. You're making it so you can get the square. So, but what we've done, we're adding on something that isn't actually there. So this half of 4 squared, which half of 4 is 2, 2 squared is 4. So we're adding on a 4 here. So we need to actually subtract that 4. And then we put the minus 7 at the end. So let's do that. So this will give us 2t squared plus 4t plus 4. So this is the square. Then we're going to minus 4, then we're going to minus 7. And now I can just neaten it up. So this is the square, so this is a squared plus 2ab plus b squared. That factorises to t plus 2, so a plus b squared. Minus 4 minus 7, it's minus 11. And well, we're almost there. And if we were solving, we wouldn't need to, go further in the factorisation, but we're not solving, so we want to fully factorise. So I'm going to put 2. And what I can see here is a squared minus b squared situation. And of course, a squared minus b squared factorises to a minus b, a plus b. So a is t plus 2. So we're minusing root 11, not 11, root 11, and t plus 2 plus root 11. So be careful, a lot of people are just going to write 11 rather than root 11. Don't forget that it's what we have in this line of working out. 11 is b squared, it's not b, so you've got to be careful of that. People are okay if it was 16 because, the square root of 16 is 4, so that's fine. But when you get something that doesn't have a nice, easy square root, people don't do so well with that. So I can now just remove those big brackets, and this is what I end up with. So this would be my final factorised form. It looks really nasty. Factorise, often people think, oh, when you factorise, it gets smaller, it looks like it's less. No, factorise just means it has brackets. So as you can see, the question here looks a lot neater and nicer than our factorised form. However, our factorised form is more useful. Moving on. So now we go to where we solve. So there's a distinction, and it's really important that you note that distinction. We have an equal sign and we will be solving here. So in this case, I'm going to cross multiply or attempt to cross multiply 3x times 2x. And let's see, 1 times negative 3. So negative 3 times 1 is negative 3. 3x times 2x is 6x squared. Let's cross multiply. 3x times negative 3 is negative 9x, 2x times 1 is positive 2x, and yes, that equals negative 7x. And again, I do the little check there to make sure that there are no silly mistakes. And now, 3x plus 1, 2x minus 3, so that's a factorised form, will equal 0. And now we can solve for each of those. So null factor law means that each thing multiplied together, each set of brackets, each term will, if one of those is 0, then the whole thing is 0, because 0 times anything is 0. So 3x plus 1 can equal 0. That means x equals minus 1 on both sides, divided by 3 on both sides, negative a third. It's one solution. And 2x minus 3 equals 0. Add 3 on both sides, divide by 2 on both sides. It's going to be 3 on 2. So these are our two solutions for x. And, in this question, we don't have to worry about any restrictions or any rejections of values, but it's always good to check back to the question and make sure there's no domain or restriction in any form. It might be a implied domain even. That might mean one of these don't work. In this case, x, the domain would be anything, can be anything. So both those solutions are just fine. All right, The next one we're solving again, and what I can see immediately is I'm not going to be able to solve this with a cross factorization. There are no factors of 1 and x squared that are going to add together to equal 8x. So in that case, I could complete the square. I think I'm going to do the quadratic formula just so we've got an example of that as well. So the quadratic formula is that thing where x equals negative b plus or minus root b squared minus 4ac over 2a. You will know this from year 11 or from year 10. We use it quite a bit, so really you should know it's not on the formula sheet. You don't want to be putting it into your reference book. Anyway, your reference book is for the CAS section. You really got to know that formula. So what I like to do first is just check the discriminant, because if the discriminant is negative, well, that means we're going to have no solution. So then it's a waste of time to proceed with trying to solve it. There are no solutions. So let's check. So a equals 1, because it's secret 1 in front of the x squared. So it's ax squared plus bx plus c is our general form. B equals 8 and c equals 1. So b squared minus 4ac is going to be 8 squared minus 4 times a times c. So this equals 60, and really for the sake of determining whether you're going to continue the question or not, it doesn't matter if it's 60 or 100 or 0.1, it's still positive, so it means we've got two solutions. So now that we know we have two solutions, I'm going to proceed with the formula. So x equals negative b, and b is 8, plus or minus root. Now we've just already worked out b squared minus 4ac. So there's no use for us to, do that all over again. We can just write the 60 in there over 2 times a is 1. So we get x equals neg 8 plus or minus 60. So that's 4 times 15. So root 4 times root 15 over 2 times 1. Well, it's just 2. I won't write the 1 again. So x equals neg 8 plus or minus 2 root 15 over 2. And let's divide everything by 2. So we're going to get x equals negative 4 plus or minus root 15. And again, this has no restriction, no implied domain, anything like that. So all solutions are relevant for x. Let's move on. So now we have some sketching. I think there's two, probably one to sketch and then one to find an equation. So sketching is not really hard. And look, I'll link a video that I made on the table of transformations for quadratics. So with a bit of luck, there'll be a little card up there now, which gives you that link. And I'll also put the link in the description, so then you can go through that. I will not be going into detail about the table of transformations here. So I'm going to rewrite this. For a start, I'm going to put that 9 over here, because, well, then I can see the transformations a little bit more easily. So I can see then that this is going to be a vertical shift up by 9 units. The second thing I need to do, and this is really important, there's a 2 in front of the x here. And look, that's a bit unusual. You don't see it much, so you might not even know what to do with that at this stage. You just take it out. So you factorise it out. And then furthermore, now we say, well, we're squaring everything here. So we don't want those square brackets. 2 to the power of 2 is 4. So now that it looks like that, that's much easier to work with, and you can see what your dilation and reflection is. You can see your horizontal and vertical shift really clearly. If you had not done that, you might have thought that the horizontal shift was 1 unit to the left. It's not 1 unit to the left, it's half a unit to the left. So I'm going to draw a bit of a sketch to start, and I'm going to say, well, my parent graph, which is my y equals x squared, is this. So if now I'm going to deal with the dilation and reflection. I'm going to do that in one go. So take a look at the transformation video. It gives you more details of this. So the 4, which is bigger than 1, is going to make it skinnier. The negative is going to flip it over the x-axis there. So this is going to be y equals negative 4x squared. And then, well, now I'm just going to move it. So the moving is going to be, this means half a unit left, and this one, which we can't really see very well, is 9 units up. So let's do that. I'll get rid of these so we can use this. So half a unit left, 9 units up, so somewhere here. And my turning point is a neg half and 9. And it's going to be something like this. So we're almost there. The things we want to include are the turning point, which we've got, but we also want to include the y-intercept and the x-intercepts. So we will find that. I'm going to do the y-intercept first, which is, of course, easier. So let's see, y equals negative. It doesn't matter if you sub into this or you sub into the one that you factorize. You can sub into any of them. It's the same equation. So 2 times 0 is 0 plus 1 is 1. So that means y-intercept equals 8. So let's pop that on. Don't forget you want to write coordinates, not just little lines with a number on it. Always use coordinates. Sometimes they'll ask for coordinates, so if you don't put coordinates, you lose marks. Sometimes they won't ask for coordinates, but putting coordinates, you won't lose marks either. So why not just always do coordinates? And lastly, the x-intercepts when y equals 0. So I'm just going to go with the original. You've got two options here. You could put the 9 in front and see that as a squared minus b squared equals 0 and factorise in that way. I'm just going to undo it, which is just as good. So dividing by negative 1 on both sides gives me 2x plus 1 squared equals 9. I'm going to square root both sides. Notice it's plus or minus, and that makes sense. There's two solutions, so you can see the two x-intercepts. So obviously we need two values. 2x equals positive 3, and actually I've left off the 1 there. And 2x plus 1 equals neg 3. So see, I'm writing them both out, so then it's easier to work with. 2x equals 3 minus 1 is 2. So x equals 1 is one of my solutions. 2x equals neg 4, so minusing 1 on both sides. X equals neg 4 divided by 2 is neg 2. So these are my two solutions for my x-intercepts, and I can just write those on. Neg 2, 0, again with coordinates, and 1, 0. And you can see it makes sense for the picture that we've drawn there. For the graph that we've drawn, we have a positive x-intercept and a negative x-intercept, and a positive y-intercept. So there it is, showing all key features, our turning point, our y-intercept, and our two x-intercepts, and the shape. Let's move to the final example, which is where we've got to determine the equation of this graph here. And look, there's lots of different types of graphs that we can have, and different ways in which we determine the equation for quadratics. So if we have x-intercepts, or if we have a turning point, or if we just have 3 random points, they will be in different forms. For the sake of this example, what we see is that we've got 2 x-intercepts, and that's important because we determine the form to be x-intercept form, and that's y equals a, x minus b, x minus c, and it doesn't matter what variables you use. I always use a for the dilation, and that will encompass a reflection. So if the graph was this way, you don't make it negative. Your algebra will make it negative by itself. So let's put the values in the obvious information, and the obvious information, the x-intercepts. So we have x plus 5 and x minus 8. And the reason it's the opposite is because, well, if you were solving this, x minus 8 equals 0, that would give you x equals 8. And that's what our x-intercept is. So if you write x plus 8, Well, equating that to 0 would mean x equals -8, and that's not the case. X is -5 here, not -8. So we will not do that. So now that we've got that, the final thing to do is to sub in the other point. And this is important and I think obvious, because they're not just going to give you a random point for no reason. Sometimes they might, but on the very, very large majority of times, the information you're given, you need to use it all. So I'm just going to sub that point in. Y is -4 and x is 0. And let's solve that. -4 equals a, 5 -8. -4 equals -40a, and that means a equals 1/10. So, therefore, our equation is y equals 1/10 x plus 5 x minus 8. And there is absolutely no reason or need to expand this. You should not. It will make it more room for error. Leave it like that, it's fine. I think that's all the examples. Yes, so that completes exercise 1.4.